Ladies and gentlemen, welcome to this lecture on wireless charging of electric vehicles. Recently, wireless charging of mobile phones has become a possibility, and one does not need to connect the charging cable to phone to charge it. This technology can be extended for charging electric car batteries as well. In this lecture, we are going to learn about the three things. What are the advantages and disadvantages of wireless charging? What are the parts of an inductive wireless charging system? And how does an inductive power transfer system work? During wireless power transfer, power is transferred from a source to a load without the need for a conducting cable in between. Different types of wireless power transfer techniques are possible based on energy carrier medium. They can be mainly classified as inductive, capacitive, microwave, laser, and acoustic power transfer. Inductive power transfer of IPT is a form of wireless power transfer that relies on the high-frequency magnetic fields. Typically, applications use frequency ranging from kHz to MHz, and power levels can range from microwatts to hundreds of kilowatts. The power transfer efficiencies can be in the range of 75 to 92%. On the other hand, capacitive power transfer relies on oscillating electric fields at frequencies of 100 kHz to MHz. Typically, applications involve low powers 1 to 50 watt with efficiencies in the range of 50 to 80%. Other modes of wireless power transfer include those that use microwaves in the frequency range of 300 MHz to 3 GHz used, for example, in space-powered satellites. Finally, there is laser power transfer using electromagnetic radiation at a very high frequency and acoustic power transfer at frequencies in the range of 20 to 100 kHz. Inductive power is the most popular method of wireless power transfer used for charging electric vehicles' batteries and will be the focus of this lecture. Inductive power transfer systems have several advantages and disadvantages compared to conductive charging. The three advantages of such systems are that we don't need to add charge poles to the streets and hence are aesthetically more compatible, especially for traditional cities. Also, the wireless charge pads in the ground can be flush-mounted buried. Further, they are safe and convenient as the electric vehicle can be charged at the comfort of parking without plugging any cable into the system, and possibilities for tripping on the cable are avoided. Wireless charging systems for electric vehicles are already commercially available today, and this is only expected to increase in the future. The main disadvantage of the IPT systems are the higher losses in the system. The cost of the system is relatively higher as well due to the additional converters and two charging pads that are needed, one on the ground and one on the vehicle. However, the power efficiency of these systems are improving and will become competitive with respect to conductive charging. Let us now look at the key parts of an IPT system and understand how it works. In the first step, the inductive power transfer system takes power from the 50 Hz AC mains, which can be single-phase or three-phase, and is rectified to DC using a DC to DC converter. Alternatively, power directly from a DC source can be used as well. This DC input is then converted to high-frequency AC power using a DC-AC inverter. The standard for electric vehicle charging earmarks a small band between 80 to 90 kHz for wireless charging electric vehicles with a center frequency of 85 kHz. The inverter produces this 85 kHz pulse with modulated or PWM voltage, which is fed to a wireless charging pad. A charging pad consists of conducting coils spread over a surface in a specific shape and may or may not have magnetic material. One charging pad is placed on the ground and is called the primary or base pad, and the second pad is placed underneath of the vehicle and is called the secondary or vehicle pad. At close proximity, the primary and secondary coil are electromagnetically coupled to each, making it possible to exchange power between them. The inverter pulse modulation voltage creates a high-frequency sinusoidal AC current and voltage in the base pad by means of resonance with a compensation circuit consisting of capacitors. The sinusoidal AC power from the primary coil is transferred to the secondary coil due to the electromagnetic coupling. The compensation circuit helps in reducing the reactive power that needs to be delivered by the source, thereby increasing the efficiency of the system. On the vehicle side, AC power from the secondary coil is then rectified using an AC to DC rectifier and regulated using a DC to DC converter to charge the electric vehicle battery. A well-designed charge pad has three important components. First is the current conducting materials, typically copper wires with low resistivity and designed for high-frequency operation are preferred. Lead wire is a special kind of copper wire that is widely used in designing charge pads, that is a spool of stranded and twisted thin wire with each strand insulated from each other. Foil conductors that are composed of thin foils bunched together can also be used to reduce high-frequency losses in the charge pad. Secondly, magnetic flux channeling materials are required. Examples of these are ferrites, which have a high relative magnetic permeability, around 640, and is hence a good conductor of magnetic fields. Finally, magnetic flux shielding materials. An example of this is the aluminum layer below the ferrite bar. The use of the shielding material is that it prevents the magnetic flux from penetrating below the ground, hereby only permitting unidirectional flux movement from the ground pad to the vehicle pad. In reality, the two charge pads can be of several shapes and can have different sizes and coils, namely circular, rectangular, as shown by the red parts of the figure. In a few cases, each pad can be composed of magnetic materials such as ferrites, as shown in the blue parts of the picture. An interesting application of wireless charging is the ability to charge electric vehicles while it is driving. This is referred to as dynamic charging or on-road charging of electric vehicles. Here, a single large base pad or multiple smaller base pads can be placed underneath the road with or without magnetic material like ferrites. Power electronic converters connected to these charging pads help generate magnetic fields, which are then picked up by the charging pad placed underneath of the vehicle. Hence, the vehicle picks up power wirelessly as it drives, and this is used to both supply the energy for driving as well to charge the battery. A useful consequence of this is that electric vehicles need smaller batteries. Further, the ability to charge while driving removes range anxiety and provides convenience for the user. On the flip side, on-road charging had the disadvantage of a relatively higher cost. The efficiency of the system is reduced when there is misalignment between the base charging pad in the road and the vehicle charging pad. The civil works to install the system underneath the roads are large, and the system requires standardization across the electric vehicles. To wrap up this lecture, wireless charging of electric vehicles is a convenient technology for charging electric vehicles. In case inductive power transfer, two charging pads, one on the ground and one underneath on the vehicle, are used to exchange power using magnetic fields. Power is exchanged at the high frequencies in order of 85 kHz, and power electronic converters are used to facilitate this. An extension of wireless charging is called on-road charging and allows electric vehicles to be charged while they are driving by placing charging pads underneath the roads.